that's the way every day goes.
Hello everyone, welcome to our ECG 565 Highway Engineering Road Safety Audit. Today we evaluating 3 critical pavement elements: skid resistance, surface texture depth, and drainage efficiency. Poor friction and drainage significantly increase the risk of skidding and hydroplaning during rain. To see how real world will impact these safety features, we testing 3 different road segments with variety traffic intensity across the UiTM Shah Alam campus. Let's get started.
Skid resistance test. Our first test measures skid resistance using a British pendulum tester or BPT. This test helps us evaluate the friction between a vehicle tires and the road surface. First, we place the BPT on the test surface and use the built-in spirit levels to ensure the device is perfectly horizontal. Next, we adjust the height of the pendulum so that the rubber slide contacts the pavement for a specific standardized length, which we verify using a measuring ruler. We then raise the pendulum to the starting position and release it. The pointer indicates the British pendulum number, representing the frictional resistance. We record the readings under dry condition first, then we simulate a rainy environment by pouring water over the test area and repeat the swing to record the wet skid resistance.
Surface texture depth. Next, we need to evaluate the macro texture of the pavement, which contributes to efficient removal of water from the road surface. For this, we use the sand patch method. We start by thoroughly cleaning the selected surface area with a brush to remove any loose debris. We then take a known volume of fine sand using a standard measurement cylinder and pour it into a single pile on the pavement. Using a flat disc, we carefully spread the sand upward in a circular motion. We continue spreading until the sand fills the surface voids and is flush with the highest peak of the aggregate. Finally, we use a ruler to measure the diameter of the sand patch across multiple axes. By knowing the initial volume of the sand and the final diameter of the patch, we can calculate the average surface texture depth.
For Danish performance, our final assessment evaluates the effectiveness of surface drainage. Good texture depth should theoretically allow water to escape, but we need to see how fast the water actually drains away. We place a specialized cylinder drainage apparatus flat against the pavement surface. Weights are added to the base to ensure a tight seal against the road. We then fill the cylinder with a specific volume of water. As the water is released to flow through the voids in the pavement surface, we immediately start a stopwatch. We record the exact time it takes for the water level to drain completely. A faster drainage time indicates a surface that is less prone to water pooling and hydroplaning risk.
Now that we complete our field testing at all 3 locations, let's walk through what the data is telling us, starting with skid resistance, then texture depth, and finally drainage. For skid resistance, we use the British pendulum tester to record the British pendulum number or BPM under both dry and wet condition at each side. Location 1 record the highest dry BPM, average 85, a strong reading where reading the range typically considered very good for asphalt surface. Location 2 was close behind at 82. Location 3, however, averaged only around 52 in dry condition, noticeably lower than the other 2. The wet readings are where it gets interesting. Location 1 dropped from 85 to about 68, a fall of roughly 20%, which is the kind of friction loss expect when the water gets between the tire and the road surface. Location 3 dropped only slightly from about 52 to 50, but location 2 barely changed at all. 82 dry versus 81.7 wet, less than a 1% difference. That's unusual, since friction normally drops severely under wet condition. This could point to a more open or coarser surface texture at location 2 that continues to channel water away effectively even during testing, or it could simply reflect natural variability in the readings. Either way, it's a result worth flagging rather than closing over. Next, we assess surface texture depth using the same patch method. We measure the diameter of the same patch left on the pavement, then use the standard formula. Means texture depth equal 4 times the same volume, divided by pi times the diameter square, to calculate the texture depth at each location. Location 3 actually produced the deepest texture at just over 2 mm, followed by location 1 at 1.8 mm and location 2 at 1.72 mm. All three sit with the typical range associated with adequate macro texture for water drainage on a varying course. For our third parameter, we measure how quickly water drains at each location. Location 1 had the fastest drainage time at 7.24 seconds. Location 2 followed at 7.51 seconds and location 3 was the slowest at 8.09 seconds. Now putting these three results side by side gives us a clearer picture and one generally interesting inconsistency worth discussing. Location 3 has the deepest surface texture of all three sites, which would normally suggest the best drainage performance, since deeper groove give water more room to escape from under the tire, but it actually record the slowest drainage time and the lowest skid resistance of the three locations.